Okay, welcome back. Excuse me. Welcome back to our channel. We're going to be completing lesson 7.3, and it's called cyclic polygons. And we're going to be solidifying understanding, meaning we're going to build and develop some of that understanding. So today you're going to be able to examine the relationship between an inscribed angle and an intercepted arc. Okay, and if you don't remember what those things are, don't worry, I'm going to explain. But you can answer these questions as well. We have seen that circles can be inscribed in triangles, so that circles touch all three sides, and that triangles can be inscribed in circles, so that the circle passes through all three vertices. What other types of polygons can be inscribed in circles or can contain inscribed circles so that circles that touch all of their sides? What relationships exist between central angles and inscribed angles that intercept the same arc? So we're really looking at circles now, and we're looking at angles within those circles, and then even later on outside those circles or on the circles. So when you were going through this, your question should always be, how are those related? All right, so by definition, a cyclic polygon is a polygon that can be inscribed in a circle. That is, all of the vertices of the polygon lie on the same circle. In centers of a triangle, your work with Kara's notes and the diagram should have convinced you that it is possible to locate a point that is equidistant from all three vertices of any triangle, and therefore all triangles are cyclic polygons. Based on Kara's work, use a compass and a straightedge to construct the circles that contain all three vertices, or at least one of the following triangles. Okay, so the way I want to try to first do this, and I don't think I can. Okay, so I'm going to try to we're not going to construct, but we are going to try and show you what they mean by those circles. So let me see if I can do this really quick. So I'm going to build, and you won't be able to see me building it, but I'm going to build circles onto here. And my goal is to try to get all the circle. Oops, that's not a circle. There you go. Oh, it's not holding a circle anymore. Hold on a second. That's a circle. Okay. And your goal is, when you're building this, is you're trying to have all of the vertices are on that circle. You can kind of see me like playing around with it. And so if I actually had a compass, this would be really good. So then my goal is to try to build a circle onto each of these shapes so that the vertices go through, or they're on the circle. So here's me doing it again. And all I'm trying to do is find a circle whose radius whose points go all through there. And that is pretty good right there. Okay, and then I would do the last one as well, and we just change colors. I think that's gonna go like that or something. Oh. Is that good? That's pretty good. It's not perfect. I think it might need to be a little tad bigger. All right, so that's my best that I got for you, where those circles and the vertices of the triangles are on top of each other. Okay, and what the whole point of that is we're going to build relationships with those angles and the intercepted arc. So, in case you don't know, they use the word inscribed angle, and so this word here, inscribed angle, here means an angle whose vertex is on the circle. I'm going to use my shorthand circle like this. Okay, so whenever you see an inscribed angle, I like calling them an onscribed angle because it's on the circle, meaning that each of these vertices here is actually on the circle. You guys all see that? Even though this one is a little bit off, I would like this one to be a little bit better. Yeah, that one's a little better. So here we have them on the circle and we have them on the circle. Okay. So that's an inscribed angle. So the inscribed angle is whose vertex is on the circle. Okay. The intercepted arc is like if we're talking about this angle here, right? Angle BAC, then the inscribed angle is going to be this part of the circle. It's the angle, it's the part of the pizza crust that is being cut out by that angle. So it's part of the pizza crust that's being cut out by that angle. Okay, since each of the vertices or vertex of an inscribed triangle lies on a circle, each angle of the triangle is inscribed angle. We know that the sum of the measures of the interior angles is 180, and that the sum of the measures of the three intercepted arcs altogether is 360, because that's what a circle is. Using one of the inscribed triangles you created, illustrate why you know this is true. Okay, so how do you know that this is true? Okay. So how do you know that the sum of the measures of the interior angles is 180 and that the sum of the measures of the three intercepted arcs is 360? Okay, that's number one. And so while you think about that, I want you to think about how do you know, like individually, those two are true, but your question to yourself is going to be again, well, how is that related? So for me, this makes sense because each of these angles here, right, add up to 180. And each of these arcs here will add up to 360 because that's what a circle is. Okay. And so again, your question is how is that going to be related later? So the degree measure of an arc is defined the same as the measure of the central angle formed by the radii that contain the endpoints of the arc. Okay, so let me just say that again. So this guy here is 62 degrees. We measure that arc as 62 degrees. It is defined by this angle here called the central angle. We call this guy the central angle because he's the angle whose vertex is on the center. Angle whose vertex is on the center. Now, you can say is the center, but I like using this word on so you know that they kind of like overlap. So, wait, Miss Johnson, what? So, whatever this central angle is, and in this case it's 62 degrees, then this intercepted arc, his intercepted arc, the pizza crust cut out by that angle is also 62 degrees. Okay. So the question is, but how is the measure of an inscribed angle, this back guy back here, this back angle here, how is he how does that relate to that same intercepted arc? How is the inscribed angle, angle ADC, related to that arc? Do you think it's going to be the same? Do you think it's going to be different? And you can think about it based on your kind of understanding here. So your understanding here was if you add up all the angles of a triangle, it'll be 180. So your triangle sum is 180. Your intercepted arc sum is 360. Now my brain, whenever I see two numbers like this, says, well, how am I going to get from here to here, or vice versa, from here to here? So that's something for us to figure out. Okay, using a protractor with your group to find the measure of an intercepted arc represented on each circle diagram in problem 1. Then find the measure of each corresponding inscribed angle. Okay, so I'm going to pause right here and come back with my protractor. Okay, so I'm back with my protractor. This is technically not a protractor, it's my ruler, but I'm going to use it to measure my angles. And what I'm going to do is I'm going to rotate my protractor here and line it up with one of my sides, and it gives me how far the angle is from 0. So it's going to measure from 0 to here. So I'm just going to have to do a little bit of math with you to figure this out. So if I go from here, I'm going to measure this here. So if I go from here to here, this angle here looks like it's 68 degrees, right? So I'm going to write that down. So this angle, let's see, let me get a vertical line here just so that you can see what I'm measuring. Oops. Thought I grabbed a line, I didn't. All right, let me move this guy down a little bit. Oh, he's not going to click into place. That's all right. All right, so I'm just going to pretend. So that's 68 degrees. Okay. And if this angle here, oh, this is going to be maybe confusing to you. So this measures off the 90. So I'm going to have to subtract. Okay, so here I'm going to show you what I'm doing. So here we measured this as 68 degrees, and we measured this angle here as 57 degrees. So how much is left of that angle? How much is left of that angle? Well, it's 180, right? So my calculator would tell me, let's see, let's grab our Desmos calculator. It's 180 minus 57 minus 68. And so we get 55 degrees. Okay, so this angle in here is 55 degrees. Okay, and so what they wanted us to do was they wanted us to measure each arc and intercepted angle. Okay, so the way we would measure that intercepted angle is from the central angle. And I'm going to have to guess where my central angle is, about maybe here-ish. It's going to have to be, looks pretty good. And then draw a line from there to there, right? So here to here. And this is all me measuring off the cuff. So I'm going to do the same thing. So that's about 34 degrees. So this is going to be kind of a mess, but that's okay. And we got this guy here, which is about 38 degrees. And then we go see what's left, right? And so we bring this back. Oops. So we get 180 minus 38 minus 34. That angle is 108 degrees. Okay. So it's not perfect because my measuring is going to be a little bit off, and so is my little center and central angle. But there's a relationship that I would really like you to see there. Okay. And so I'm gonna do one more, and maybe you'll see it more with this one. And so I'm gonna take it to this one. So this angle here is 22 degrees. And this angle here is 65, 67. So this is going to be 22 degrees. And this angle here is 67 degrees. Let's see. Oh, it's 68. My bad, 68 degrees. And then if you notice, these two lines are parallel. So this is going to be 68 degrees too. So if you add 68 and 22, you get 90 degrees. So this is a 90-degree angle here. Okay. And your center is here. So if you measure this angle here, this angle here is 180 degrees. Do you see a relationship? Let me erase all this. Do you see a relationship between your central angle and your inscribed angle? And again, here's another relationship that you can stand on. I'll be right back. Okay. All right. So one of the measures. So as you think about this, one of the things that you're supposed to get is that the measure. So here, so your measure of your central angle equals your measure of intercepted arc. Okay, this is a truth. Okay, know this one. Oh, you cannot see what I'm writing. Give me 1 second. Sorry, I was writing over here and you can't see me. Okay, so then what I want to do is I want to talk about the measure of the central angle. Oh, not central angle, the inscribed angle. Okay, and if you look at the trend that I see the measure of the angle is 90 and the measure of the arc is 180. I see the measure of the angles add up to 180 and the measures of the arc add up to 360. And some of you already figured out the relationship. So the measure of the inscribed angle is half. I'm going to write this as an equation. Equals half of the measure of the intercepted arc. So here's another thing. So I'm going to put this in a giant bubble because this is something that you need to know going forward. So the measure of for the measure of the central angle, it's the same, 62, 62. So now you can figure out this measure back here. Well, if the measure of the angle is half the arc and the arc is 62, so I'm going to put 62 here, take half of it, and that's the measure of that angle. Oops, measure of angle. Yeah, I can put measure of angle D. So measure of angle D is half of 62, which is just 31 degrees. So this guy here, oops, can't see it, 31 degrees. So we're just going to take half of it every single time. Okay.